the first homework is due today. It has 11 questions on it, and I'm sure you have questions on at least some of them because some of them we haven't really looked at the material. And so let's start the class by just saying, okay, choose like 3 homework problems that you have a question about, and let's look at them before we get started with the regular lecture. So when I look up, if I see hands up, that's who I'm going to. Okay, see Leslie, Danny, and Ivy. Okay, so Leslie, what was your question?
Number 8, like as in like I have no idea. Like after A, B, C, and D just don't like. I even asked Alex, and Alex was having trouble with it too. Like, wait, what? Like, there's no start, there's no this, or I don't know.
Okay, now when you look at these, by the way, the RC, that's telling you which type of question it is. I don't remember what reading comprehension or something is what RC stands for. The PAC, I don't remember all of them, but I figured I'd put those in as prefixes so you know which types of questions they are. And so number 8, a TAS, I don't know. A ball is thrown straight up with enough speed so that it is in the air for several seconds. What's the velocity of the ball when it reaches its highest point? Okay, so we have the ball goes up, comes back down, and it asks us what's the velocity right there. So I throw this up, comes back down. What is the definition of velocity? It's that was acceleration. So not bad. The 2 things that they said were change in speed and change in direction. Those are the 2 things that are accelerations. Okay, acceleration and velocity are tightly aligned because of that relationship. Velocity is the rate of change in position. So for instance, when the ball is going up, its position is going from here to somewhere higher. And so you take the distance it traveled divided by the time, and that gives you the speed. And the fact that it was going up gives you the direction. So going up, it had an upward velocity. Coming down, pretty soon you realize, wait, he said coming down. What's the velocity like? It's going, what direction is it moving when it's coming down? Down. So it has a downward velocity. Now, when it's going up, what's happening to the velocity? Is it going fast? That's the speed part. Is it going faster or slower with time as it's going up? It slows down. So it has an acceleration, a change in velocity that is in the opposite direction it was traveling because it's slowing down. So as it's going up, the acceleration is downward. Now, as it's coming down, what's happening to its speed? Speeding up. So that means it has an acceleration in the direction it's traveling when it's coming down, which is down again. So what we've established so far, which is probably all the questions that are going to be asked, we said at this location, its velocity is up. At this location, its velocity is down. But the acceleration here was down and the acceleration here was down. That's what we said so far. The acceleration was down when it was going up, which meant it was slowing down. The acceleration was down when it was coming downward, which meant it was speeding up. The first question was, what's happening at the tippy top? So what is the velocity of the ball when it reaches its highest point? It's momentarily 0. Now, some people say, how could it be 0? Because that would mean it's not moving. For a split second, it's not moving. That's what it means. It's true. Because it was going up and then it's going down. Between going up and going down, it has to stop. So the answer at the top is the speed is 0. So that's the first question. The speed is 0 at the top. Now remember, in your answers, if you just put 0, you're not going to get credit. You have to have some explanation of how you got there.
For your explanation, would you want something like for that split second, it has to change its direction from up to down so that it momentarily it's at 0?
That would be perfect,
Okay.
Leslie. Okay, next question. What is its velocity 1 second before it reaches the highest point? So based on what we already did, we know its direction, the direction before it reaches the highest point, what direction is the velocity? Up, right. Now it gives us a specific about what its velocity is 1 second before. And that's going to require us to go to math. So if I have this thing flying through the air, we establish the acceleration is down when it's going up and down when it's coming down. What is the acceleration of the object when you drop it? 9.8 meters per second squared. If you want to use 10, I will accept both answers, okay? The textbook uses 10 to make it easier. Remember I said because they figure you guys are going to have a hard time with 9.8. So I'm going to go with the 9.8 because that's what that's what. It's Gabby. I have to look at your name here. I know. That's what Gabby said. So we're going to use acceleration is equal to G is equal to 9.80 meters per second squared. It's actually a vector, so I'll put the arrows over it and the direction down. And then we have our equation that defined acceleration. Acceleration is change in velocity over change in time. Remember, I told you I'm really, really comfortable with these symbols, but these symbols are new to you. So I'm saying the words as I write the symbols, and hopefully that's helping you to tie the symbols to the words so that they start becoming meaningful to you instead of just, wow, he wrote something. If we expand this, the change in velocity will be velocity final minus velocity initial. And then I'm still going to put over the change in time. So that gives me an equation I can now solve to find the velocity difference between two times. So I'm going to do that. And because the math requirement for this class is pretty minimal, I'm going to actually go through the one-step algebra for solving this equation for the change in speed, or change in velocity, excuse me. Remember I told you I make that mistake. I want to get the velocities not divided by change in time, so I multiply them by change in time. But what I do to one term, I must do to all the terms. And so that gives me an equation that says the velocity final minus the velocity initial is equal to the acceleration multiplied by the change in time. Now, in our situation for part B, we're asked for the velocity 1 second before it reaches. That will be my velocity initial. And then its highest point will be our velocity final. So the velocity final, what was the velocity at the highest point? So 0 minus velocity initial equals acceleration times change in time. So move the minus sign across. The 0 I can just erase, right? Multiply everything by -1. So I have the velocity initial is equal to minus acceleration times change in time equals minus acceleration 9.80 meters per second squared down, multiplied by the change in time of 1 second.
Is it -1 because of the 1 second? Or why is it negative? What is
This negative sign is because of, I'm going to change color, because that negative, I wanted to get rid of it, so I had the V initial without the minus sign. So it had nothing to do with the direction of gravity or the time. It was from the equation. So 1 times 9.8 is not tough. Notice the units. Meters per second squared times seconds. That allows me to cancel one of the seconds. And so I'm going to get minus 9.80 meters per second down. That's a correct answer, but it's a clumsy answer. Because what direction is minus down? Up. And so it'd be much more comfortable to write equals 9.80 meters per second up. So that's its velocity 1 second before it reaches the peak. Part C, what's the velocity? What's the change in its velocity during this 1 second interval? Yeah, question.
So that's what I wrote down, but do you want to show the calculations?
Yeah.
And like the explanation is gonna be the like, I don't know if this is incorrect or not. I just put because it is the velocity. It is 9.80 because it is the velocity when it is slowing down right before it gets to the zero. Like
You would need to be clear because, you could have had 5. It goes through 5 before it gets to 0 as well. But it's specific to 1 second. So you need to have the calculation for what will it be 1 second beforehand. So you should have somewhere a calculation that looks like this. Now, once you've done part B, part C is simple. What's the change in velocity? Change in is final minus initial. So since we just calculated the velocity 1 second before, our final is 0. Our initial is what we just calculated of 9.8 meters per second up. So the change in velocity is going to be 0 minus 9.8 meters per second up, or 9.8 meters per second down. So the next one is just a simple which of course is 9.80 meters per second down, was the change in velocity. And of course, we actually had done the calculation. This here was change in velocity right there. Right, so it's pretty clear. Is that the one you were asking about? Part C? Or was it D?
yeah, because then the thing that confused me is that then it says starts saying, it's velocity after reaches 1, and I kept thinking 9.80 for many of them and just the negative changes or something. I don't know, but I feel like it's wrong. I don't know.
Well, now the next one is asking what happens 1 second after the peak. So 1 second after the peak, now our velocity initial is going to be at the peak, and our velocity final is going to be 1 second later. And so I come back to the calculation that I did here, and the only difference is, because I erased it, that was 0, the velocity final. So for part D, we have velocity initial is 0, and we look for velocity final. So you just put in the velocity initial is 0 here, the velocity final is what you're looking for. The A is the same, the delta T is the same, and so for D, no minus signs to worry about now. There's our speed 1 second after. We did the same calculation. It's redundant to make sure that you start to feel some comfort with it. And then E, what is the change in velocity in this 1 second interval? Well, take the final, 9.8 meters per second down, minus the initial, 0. You get 9.8 meters per second down, which is the same as you had for the 1 second before, because the acceleration throughout the flight is 9.8 meters per second squared down. Now, the last part is, what is the change in its velocity during the 2-second interval from 1 second before to 1 second after. And notice there's a word of caution. So what is change in? What do we always use for changing? Changing is blank minus blank.
What?
The order, when we do a change in something, it's the value at some time minus the value at no time. Which one comes first? It's always the final minus the initial. So what was our final velocity? Our velocity is 1 second after the peak. Is what?
Negative 9.8.
Okay, by negative she means it's down. And so that's perfect to say it's negative 9.8 meters per second. If we define up as positive, that's perfect. And what was it 1 second before reaching the peak? It was positive 9.8 meters per second for the speed. So if I take the difference, the final one, minus 9.8 meters per second, minus the initial one, which is 9.8 meters per second, I end up with, I'll write it down because as you say it, it doesn't seem as clear as when you write it down. So there is the final minus 9.80 meters per second up using the signs like Ivy did. And then I have minus, and then the initial was 9.80 meters per second up. But notice they both have a minus sign. So we put those together and that's going to be equal minus 19.6 meters per second up. Right? It's not zero. That's why the caution is there. So you realize it's not zero. The speed was 9.8 meters per second in both cases. But the velocity has direction. So initially it was upward. In the final it was downward. You take the difference, and the difference came to be a downward value of 19.6 meters per second. Okay, any questions about that one before I move to Danny's question?
19.6 by multiplying?
No.
No, by what?
Minus 9.8 minus 9.8. Subtracting.
Oh, it's like adding them. Okay. But it's adding.
Okay, any other questions on this problem? Okay. Danny, what was your question? That was your question. Excellent. Ivy, was that your question? Oh, wow.
Yeah,
Knocking it out of the park here. Okay, let me add one more thing to this. I skipped one thing. It didn't ask it. I did the velocity and acceleration going up and coming down and the velocity at the top. What's the acceleration at the top? Okay, that is the common answer. It's not correct, but it's the common answer. That's why I asked the question. Because I'm guessing most people were thinking zero. Because you know that it's momentarily stationary at the top. The velocity is zero. And we get velocity and acceleration confused. As much as we study it, we still get them confused. Because in your car, you just think, I want to go faster, I press the accelerator, and you think acceleration fast. Acceleration causes fast, but it's not the same thing. So acceleration, we've learned this definition, is the change in velocity over change in time. If the acceleration is zero, what does that tell you about the change in velocity? Well, the change in velocity.
Okay.
Since acceleration is change in velocity over change in time, if acceleration is zero, change in velocity is? You're not following, are we? If A is zero, if the left side of this equation is zero, then what is the right side of the equation going to have to equal? Zero. And so what does that tell you about the change in velocity? It's zero. The only way for the right-hand side to be 0 is either if time is infinite, which we're not going to wait an infinite amount of time to see if it ever moves, or if the change in velocity is 0. So that means if the acceleration is 0, the velocity is going to remain constant. So we said its velocity at the peak is 0. If its velocity were to remain 0, what would it all be doing? It'd be hovering. Well, that's not what happens. You throw it up, it comes down. So it can't have a 0 acceleration at the peak. It has to have an acceleration that's going to make the velocity change. What direction was the velocity changing? It went from up to down. So what direction was it changing? In the downward direction. And in fact, the acceleration at the top is exactly the same as the acceleration everywhere else as it's flying through the air. If we can ignore the fact that we have air around us, air resistance, the acceleration remains 9.8 meters per second squared down the entire time it's flying through the air. Now, air resistance for this ball, we tend to say is minimal. Although if you play tennis, you know that the air resistance is reasonably significant, right? You give it like top spin, and it will go and dive down over the net if you did it right. If you're me, it just hits the net. But you know, if you did it right, it'll dive down because it has a significant interaction with the air. But if it's going slow, the slower it is, the less significant that interaction is. Okay, well, everybody who raised their hand wanted the same question.
Oh, it's the same question. So then for E, there's just a change in velocity during this 1 second interval, is it still 9.80 at that point?
The acceleration will be 9.80 meters per second.
Yeah.
So every second, the speed will change by 9.8 meters per second. So if we'd gone to what's the speed 2 seconds after it's at the top, it would have been 2 times 9.8.
Okay. Oh, awesome.
Okay, now a few more things about the homework. Yes, don't forget this up here about putting in explanations for everything. When is the homework due?
5.
Or?
No.
It's at 5 if you're turning in on paper. It's 11:55 if you turn it in on Moodle. If turning in on Moodle, it has to be a single file that's a PDF file.
Are you okay with scanning?
I'm okay with scanning it. I need to be able to read it. That's kind of an important thing. So you have 2 different due times. One is because I need to collect the papers. That's why it's 5 p.m. if you turn in a hard copy. If you turn it on Moodle, I give you until midnight. So you have time to look over, to talk about things, to assimilate what we've done in class today, and especially like going through a problem here before it's due. If you've already turned it in on Moodle and you want to update it, you can only have 1 file, so you have to delete the old file and upload a new one. So you can do that up until the due time. Of course, you don't want to be at the last second, delete a submission and not have time to put the new submission up. So be a little careful with your time there. I don't have my office hours posted on my office, but they are in your syllabus. I will be in my office from 1 to 4:30 today. I'll actually be doing a heart scan thing with the student today because we couldn't do it on Monday. So I'll have a student in there doing the heart scan thing from 3:30 to 4:30. So if you can come before 3:30 and after 1, I'll be there to help you. And it's roughly the same times on Mondays for my office hours, as well as from 8:30 to 9:30 every morning, but Thursday morning. And if you ever come by and I'm in my office, we've covered most of the hours since I'm in class most of the other times. But if I'm in my office, don't hesitate to come in and ask questions, right? Because I live to help you. Now, I don't have a tutor for this class, at least yet. I will try to make some inquiries on that because I had a student ask about that. And we do want students to have whatever resources they need to be successful. You can also email me, to contact me and ask questions. So I want to make sure that you get what you need. If you think, I need something else, come talk to me. Don't just say, oh, looks like I'm out of luck. Do you have a question? No. Okay. I thought it looked like you might. I do. Okay. For submitting on Moodle, I don't recall if I actually showed you how to submit on Moodle or not. So let's go there. So you go to the class in Moodle. Of course, you have to log in. And I'm logged in. Yay. Go to the class. Did I show you this already? We go with no. Nobody said yes. And so you find the assignment whichever way you want. You can look on the calendar on the 17th. We have the homework. That's one way. You can just look for the homework. Here's the homework assignment. I don't know why the graphic is not showing up. It's there. This morning on my other computer, it didn't show up. I reloaded it and it showed up. There is a picture for number 9. If it doesn't show up, well, you do have your textbook as well. So to put your submission in, oh, I know why probably. Because I'm not actually in the homework. Here we go. If you actually go to the homework, it's there. It's when you're in the calendar preview that it didn't show it. Now I understand. Okay, so if I want to submit an answer, you're going to have a button here that says submit your answer. And it tells you how much time you have until they're due. So, see, it says 5 p.m. and 6 hours, 32 minutes. That's not really an That's the time until it has to be turned in at my door. But you still have until 11:55 to turn in online. So it has that it will accept them online until 11:55, but it shows the due time is the time that it's due under my door if you're going to do it that way. So just be really clear, that time is just when it's due under the door, 11:55 if you're doing it on Moodle. So there'll be a button right here. You click it to submit. You just drag and drop your PDF file. It will only accept PDF files. And then make sure you do hit submit. There have been cases, my son last semester, where people dragged it in there and they said, yay, I'm done, and closed the browser. It's not done until you hit submit. All right, let's go to I know I said 3 problems, but I did take up more than half the class period on that one problem. So logic dictates that if I were to do 3 problems, we wouldn't have a lecture today. So continuing looking at Newton's laws, which will help us with problems like the monkey one. And our first clicker question, oh please, oh great clicker gods, let this work today. It's channel 33, or if you're using your smartphone, it's web SCNC. A little worried because I don't have any answers yet. Has anyone tried? Okay, there we go. When things don't seem to be working quite the way I like. So when Nellie pushes a crate across the factory floor at constant speed, the force of friction between the crate and the floor is... Yay! Is it on the right channel? Oh, okay. You apparently have a different clicker than the one that's registered, but I got the right number of answers, so I assume that it took yours. And of course, it did not show me how many people answered what. So I guess we won't look at the answer numbers that you gave. It's also showing that there's something really weird going on with the software. This is a new version because other things weren't working last one. What was the most popular answer? It didn't show you either, did it? Well, let's just go to the correct one. In this case, it's moving at a constant speed. Now, I believe last class period we got to Newton's second law, didn't we? We had that the... Okay, well, this is a first law question, but I always like to use the second law. What's the difference in the first law and the second law? The first law said that an object stays in constant motion That means constant speed and constant direction, unless there's a net force acting on it. So we can take the first law and say, is that constant motion? It's constant speed. We assume it's in the same direction. It doesn't say she's going in a circle. And so we say, aha, she is traveling with constant motion, so the net force has to be 0, which we call equilibrium. And if the net force is 0, the net force is adding them all up. Now, when we're going to do a problem like this, we always draw what we call a free body diagram. A free body diagram is a diagram that shows the object we're interested in. So in this problem, what object are we interested in? Okay, the answer is the crate, because we have the friction acting on the crate, we have Nellie acting on the crate, and we're asking to compare those two. So since those two forces are both acting on the crate, our object we're interested in is the crate. That's the first difficulty with a free body diagram, is determining which object you're interested in. Once you have that, then you're going to show all the forces acting on that object. So here's the crate, and I say, okay, what forces are acting on the crate? So start naming them. Okay, friction, what'd you say? Okay, Nellie's push, so I'm going to draw those two first. What direction is Nellie pushing? She's pushing to the right, so I'm going to put an arrow like this, and I'll put force P for push. You can name them however you like. I always use a capital F if it's a force, and then a subscript to tell me which one it is. I didn't use F sub n, because I reserved that one for a special force, right? Because Nellie starts with N. That's why I didn't use it, because it's reserved for something special. Then you said the force of friction. It's sliding along. What direction is friction going to act on something that's sliding? Opposite the direction it's sliding. So that means I have the force of friction is acting like this. Okay, so that's two forces. Any more forces? There are more forces. There's a force of gravity pushing down on it. So I put F sub g for the force of gravity. Our textbook uses W generally, which to me just really obfuscates things. So I put F sub g there. And we know F sub g is the only one of these we actually know. The force of gravity is mg. And then there's one more force. What's that last force? Okay, the support force, or the normal force. That's where I use F sub n. It's the force to keep it from falling through the floor. So we have those four forces. And now we say, if we add all those forces up, what do they have to add up to? 0, because it was in equilibrium. Now, two of the forces are vertical and two are horizontal. This brings a very important point, something we call independence of motion. We can take directions that are perpendicular to each other, and the motion in one of those is independent of the motion in the other. So I can take Newton's second law and I can apply it in the vertical direction as well as the horizontal direction. So we always use something to define our directions. X is the horizontal, Y is the vertical. And then I say sum of the forces in the Y direction equals 0 because it's an equilibrium. And I look at my diagram and I say, what arrows do I have that are pointing the same direction as my Y arrow? And so you look, what arrow is the same direction as the Y arrow? Force normal. So that one's one of the forces in the Y direction. Then there's one that's pointing opposite to it. Which one's pointing opposite to it? Gravity. So I put minus because it's opposite force of gravity. The other two are perpendicular, so they don't matter. Is equal to 0, which tells us that the force normal is equal to the force of gravity in this case. Remember, I made a big deal last class period about not always. But you'll see it so often, you start to think maybe it is. So that's why I had to caution it's not always. Then we shift to the X direction, which is the one you used for this problem. And of course, I didn't expect you to do all this work in answering it. But I'm doing all this work to make sure the ideas of why the answer came out are in your head. So I look in my picture, my x direction is that way. So which arrow is parallel to the x direction? So that's f sub p is positive. And the final one, f sub f, is anti-parallel is the word for it. So that's going to be minus f sub f equals 0. So force push must equal the force of friction. Now, if I was answering this question on homework, such as you do with the monkey hanging on the vine, I would say it's in equilibrium because the velocity is not changing, and thus the net force has to be 0. So the two forces that are acting in this case, the horizontal direction, have to be equal magnitude and opposite direction so that they add up to 0. So I would put all words in there if I was doing the answer. But to explain it to you, I did all of the calculations while I said the words, so you can see that it mathematically works out. It's not just I said some words and that gave me a magic answer. In physics, words can be thought of as magical, but equations, that's concrete. So do you understand why the push was equal and opposite? Good. Now the term acceleration. I talked about Galileo and the Leaning Tower of Pisa, which is probably something that never really was an experiment. It was simply a think about this, what would happen experiment. What he really did was experiments with balls rolling down planes, measuring the acceleration, how quickly it's changing speed as you change the angle. One thing we like to do a lot is drop objects. In physics, we love to drop an object and measure the time. This picture is showing, it's actually kind of confusing to look at. Those meters are supposed to be measuring the speeds at 1 second intervals. The dots are showing the positions. What's confusing about this is the spacing. Here is 0 seconds. So that time goes with that position. Here's 1 second later, goes with that one. 2 seconds later, 3 seconds later, 4 seconds later. Right? The clocks, usually we draw the pictures with the clock falling at the speed, so it's showing the same position. Notice that the space between the distance it travels in the first second is much less than the distance it travels in the second. Why? Because it's going faster in the second second than it was in the first second. Faster, bigger distance per time. And so the distances it travels each second are getting bigger and bigger and bigger. The speed changes is what we just did in the homework. We know that delta V, and I'm just going to do it without the vector sign now, is equal to A delta T. That was taking our definition of acceleration, solving it for delta V like we did in the homework. And so if we have a 1 second interval for each one of these, the change in speed is going to be the same because it's just going to be 1 second times the acceleration. So if it's falling at 9.8 meters per second squared, then the speed's going to change by 9.8 meters per second every second. Now in this picture, he once again used 10 for the acceleration of gravity. So the first picture shows it starts at a speed of 0. After 1 second, its speed is 10 times 1. After 2 seconds, its speed is 10 times 2, 20. After 3 seconds, he doesn't show it. What would it be after 3 seconds? It would be 10 times 3 is 30. Wow, good job. And after 4 seconds, 40. And after 5 seconds, 50. Right, so the speed is increasing at a linear rate. So in lab last week, you were walking back and forth and measuring the position and looking at graphs. If I was going to make a graph of the position as a function of time, And my position is going to be the distance down. So they're going to be positive distances here. It's going to start at time equals 0 at 0. After 1 second, it's just moved a little bit. After 2 seconds, it's moved much more. After 3 seconds, much, much more. And I get a graph that looks like this. It's a parabola. I had a constant change in speed, which resulted in a non-constant change in position, which matches, of course, what you see in this picture. And in just a moment, I'll introduce the equation for calculating what the distance will be. But I could have made a graph that had the velocity. Okay, let's versus time. And then I had 0 at 1 second, it was 9.8. At 2 seconds, it was 2 times 9.8 or 19.6. 3 seconds, 29.4. 4 seconds, 39.2. And that forms a nice straight line. So we have a straight line relationship for the velocity versus time when it has a constant acceleration, because velocity is acceleration multiplied by change in time. The slope of this graph is the acceleration, just like the slope of our position versus time. Because if you do the slope, the rise is change in velocity or change in speed. The run is change in time. And by definition, change in velocity over change in time is acceleration. Now, I didn't use vector signs. I should have used vector signs. And so the slope of a velocity versus time graph is acceleration. Now, your graph is actually one-dimensional, so it's speed in one direction over time, but you get the same outcome. So this is a discussion of free fall. If a falling object gains, okay, start. Wow, I'm having some problems with. Okay, well, I can make it do it. It will now accept your answers. I'm going to spend some more time playing with this software. The fact that I've been using it for years doesn't mean that the new version I know. If a falling object gains 10 meters per second, each second it falls, its acceleration is okay, I've all answered. Please be there. Yay! Okay, so we had 5 people said 10 meters per second. 2 said 10 meters per second. 0 said both, and 1 said neither. Obviously, I'm not going to put you on the spot. Well, except for the person whose name is Ivy. So what? Okay, so Ivy, what was your answer and your reasoning?
I put A.
Okay, what was your reasoning?
I was kind of confused at first because I didn't know there was a difference between A and B. Then, I don't know. I was confused. I was torn between A and B.
Okay, torn between A and B.
Yeah.
Okay, here's our key for answering. The difference between A and B is the units. What has units of meters per second? Okay, so that's speed or velocity, right? Because speed is the magnitude of the velocity. So speed or velocity has units of meters per second. What are the units of acceleration? Meters per second squared or meters per second per second. So this one here had the right units. That's why it was the correct one. Here is a table that shows the calculation of the distance and the speeds. I am not going to have time to do any problems. I will show you the equation for the distance now. The distance, you calculate, okay, what's the average speed in a second? And you can go through and do some math to find this equation. Or you can use calculus and find it really quickly. For a class of this level, we actually do neither. This level, we tell you what the equation is and tell you, take it on faith, which you should know by now. You're a college student. You are here to learn, not to be indoctrinated. Indoctrinated is telling them, believe what I tell you, right? But in a class like this, that's what we do. We say the change in position, that's a really funny way of writing it, is equal to the initial speed plus one, or multiplied by time, plus 1/2 the acceleration multiplied by time squared. So for a falling object, if the initial speed is 0, then we would have, for the case of the falling object, and the initial, whoops, that's time. The initial position is 0 and the initial speed is 0. Then we're going to have delta x is equal to x final minus x initial, and that x initial is 0, is equal to v initial t, that v initial is 0, plus 1/2. The acceleration is downward, so we usually put minus 9.80 meters per second squared, the minus sign to indicate downward, multiplied by time squared. Now for his numbers, he used 10 instead of 9.8. So 10 divided by 2 is a very simple number, 5. So for his calculation, he has 5 times multiplied by the time squared. So 1 squared, 5 times 1. 2 squared, 5 times 4. 3 squared, 5 times 9. 4 squared, 5 times 16. That's how those numbers were calculated. Question, Ms. Lopez.
On homework, when you wanted us to calculate, like show that this is a distance, did you want us to do it this way, or did you just want us to do the multiplying that the textbook shows? Either way,
Let me look at which problem you're talking about.
7. Total distance covered.
Lillian rides her bicycle along a straight road at an average velocity v. Because it says an average velocity, we say, okay, no acceleration problem. We just have the velocity is defined as change in position over change in time. So multiply both sides by change in time, change in position.
The total velocity multiplied by the distance.
The time.
Oh, sorry, time. Sorry, I meant to say time.
Yeah, so that's how you're doing it.
All right, awesome.
Okay, and that actually brings us to the end of time.